Welcome back, everyone. We're in section 7.7 now, which is the last section of chapter 7. We're going to be reviewing indeterminate forms and L'Hopital's rule. It kind of fits in with this chapter because our indeterminate forms are going to require logarithms. So that's going to kind of pop up. But other than that, this should feel mainly like review. So just a couple of examples up at the top here. These you can work out on your own. So these are all limits that we could work out algebraically. So we'll note for this one, we'll get -7 when we evaluate. For this one, we could factor, zoom in a bit here. We could factor this as a difference, or we could factor the 3 out. And so we get 3, and then x squared minus 9 would factor as x minus 3 times x plus 3, cancel out that problematic whole, and then we would end up with 3 times -6, which is -18. And then similarly for this exponential example, it's just a difference of squares on the top. So we'd have e to the x minus 1 times e to the x plus 1 all over e to the x minus 1, again getting rid of that whole value in our graph. And then we'd be left with e to the x plus 1 at 0 is just going to be 2. So we have all of these methods for kind of working through these examples that if we just did direct substitution gives us 0 over 0. And 0 over 0 is kind of the most common indeterminate form. The first one would also be infinity over infinity. So that's what we're looking for, is showing that our limit would be 0 over 0 or infinity over infinity, and then we'll apply L'Hopital's rule directly, which says that the ratio, the limit as x approaches c of f of x over g of x, that ratio limit is going to be equivalent to the limit of the ratio of the derivatives of each one of those functions. So not the quotient rule, but literally the derivative of the numerator over the derivative of the denominator. And that will occur if we have an indeterminate form. So for L'Hopital's rule, again, there's some more information there you can read through to kind of review, but I think we can probably just jump right in. So we'll note for each one of these, we want to start with figuring out if it's indeterminate or not. Clearly, number 1 is going to be 1 minus 1 over 1 minus 1, so we get our 0 divided by 0. So then, by L'Hopital, we're going to get that this is equivalent to the limit as x approaches 1 of 9x to the 8th over 5x to the 4th. And then we'll get some nice cancellation, but really we could just directly substitute as well. And we'll end up with 9 over 5. For number 2, we can check the same value. So we'll get 0 over 0 if we do direct substitution. So then we can use L'Hopital. So we'll get the limit as x goes to 0 of 4 cosine 4x over 5 secant squared 5x. And then now we can directly substitute, and we'll see that we get 4 times 1 over 5 times 1, which is 4/5. Okay. Now let's go ahead and take a look at number 3. So for number 3, we've got pi from the left, so we've got 0, and then 1 minus pi from the left is going to be -1, so 1 minus -1 is 2, so this limit's just 0. So again, you always want to check that indeterminate form before you start differentiating stuff, so clearly this is just going to be 0. For number 4, we've got tan h minus h over h cubed as h goes to 0. So that's going to be 0 over 0, obviously. So then we can apply L'Hopital. So by L'Hopital's rule, let's see what we get. We're going to get the limit as h goes to 0 of secant squared h minus 1 all over 3h squared. Okay. So then if I look at that, direct substitution gives me 1 minus 1 over 3 times 0, so I get 0 over 0 again. So now I need to apply L'Hopital again. Now you could try to factor and move stuff around. Doesn't look like there's going to be an obvious factoring that helps us. So we'll do L'Hopital again. So we have the limit as h goes to 0, so the derivative of secant squared is going to be 2 secant h times secant h tan h, using the chain rule, all over 6h. Okay, so now if we do direct substitution again, it looks like we might need to apply L'Hopital again, but actually we can kind of rewrite this a little bit. So let's note that this is going to be 2 secant squared, and then tangent I'm going to rewrite as sine h over 6h cosine h. And then what we can notice here is that we're going to get that special trig limit, sine h over h. So this is going to be the limit as h goes to 0 of 2 secant squared h over 6 cosine h times the limit as h goes to 0 sine h over h, which we can split the product since both of those limits exist. And on the left we'll get 1/3, so 2 over 6 times 1, so our answer is going to be 1/3. So again, be on the lookout for some of those special trig limits. The other one is cosine h over h is 0, so look out for that as well to show up possibly in the future. All right, so then the last one we have here is the limit as x goes to infinity of natural log over the cube root of x. So this is going to be infinity over infinity, and both of these are pretty slow growth functions, right? So the cube root of x looks like that, the natural log of x looks like that, so they're not growing very rapidly, so we can't really tell the difference between their size, obviously. So let's try L'Hopital's rule. So we'll get the limit as x goes to infinity, 1 over x over 1/3 x to the negative 2/3. Which is same as just x to the negative 1. So we could then use properties of exponents to try and simplify this a bit. So we're going to get 3, because the 1/3 in the denominator will reciprocate. And then we'll have x to the negative 1 minus negative 2/3, which gives us x to the negative 1/3 still. So we're going to have x to the negative 1/3. Oh, sorry, and we're approaching infinity. So as we go to infinity, that's going to go to 0. So what that's telling us is that the cube root function is going to grow faster than the natural log function, which is going to make it approach 0. All right, so again, just kind of preliminary review, L'Hopital rule problems. Now we're going to get into the more complicated versions where we have to kind of manipulate a little bit more. So these are the indeterminate products and then other indeterminate forms. So we've got quite a few to look at here. So I'll stop the video here, and then we'll come back for part 2. So again, if you have questions, feel free to shoot me an email, come by the office hours. Otherwise, till I see you next time.